In the last section, we ended after having downloaded a file containing the results of a query. I mentioned that this comma-separated value file, so a CSV file, could be used as part of your code. In this section, we will look at a number of examples showing how to access the SDSS SkyServer database with Python. There are a number of reasons why you might like to access a database directly from your code. In fact, it is the case for most online stores and other secured websites. For example, when you log on to a website, your username and password are generally matched to the content of a database via a backend server. If the query matches something in the database, you will be able to log in. Otherwise, you may be requested to register. By integrating the database access within our code, we can simplify the overall workflow. By doing so, we will avoid having to move from one place to another. For instance, having to go to CAS jobs to get our data and then import the CSV files in our project. Therefore, we can be better organized and have a better overview of how our project is constructed. It can also increase our productivity. By having a direct access to the results, it is possible to use it directly for pre-processing, analysis, and visualization purposes. In the following examples, we will be using the Python language, which has a growing user base within the astronomy community. It is possible to do the same type of work using other languages too. In Python, different solutions are available to query databases. One example is AstroQuery, an AstroPy affiliated package. It is an astronomy-specific package that implements an application programming interface, or API, to connect to a number of astronomy databases like Simbad. It abstracts most of the SQL so that you only need to specify minimal information like the constraints of your query. Other packages like AstroML, a machine learning package, includes minimal functions to query databases. Finally, the SQL Alchemy package is intended as a complete solution to connect to databases like SQLite or MySQL directly. For detailed information, I invite you to have a look at the documentation of the different packages. As the SDSS database can be queried from the browser, it is possible to construct URLs, the address that you can see in the address bar of the browser, matching the address template used by SkyServer. In fact, SDSS provides a small Python package to do just that. The file can be downloaded at the following address. The Python exercises will be performed in the Jupyter notebook. All the information about how to set it up using the ADACS Docker is available on the LMS website. While the SQLcl script can be used by itself as a program, we will only use two functions from the code. The way the file works is by creating a structured URL so that we can ask information to the server directly. In web development, this is common practice. For example, when asking something to Google, we note that the query is included in the URL, the q equal SDSS part of the address here when searching for SDSS. This is what the query function of SQLcl does. As the default address in the original file is no longer valid, I modified it so that it points to the xsql.aspx file of the data release 13. After removing the comments from the SQL query, using the filter comments function, a URL is constructed using a key-value structure where CMD will include the SQL query and format will specify the format of the results we want to retrieve. These are then added to the end of the address following the question mark symbol. Finally, the query is sent to the address using the urllib package with the function urlopen, and the result is returned for following operations. Simple. Before we start the examples, we need to import the packages we need. In particular, we import the SQLcl package that we just discussed, along with a few extra packages like Pandas to manipulate the data, AstroPy to deal with the fits file and units, and matplotlib to plot. In the notebook, blocks of code can be used to both type in code and add comments via the markup language. To execute a block of code, you can either click on the button with the play symbol or press Shift and return at the same time on the keyboard. So, we import our packages by running the following blocks of code. I also set matplotlib parameters to increase the font size using the RC module. Our first exercise simply consists in querying the database. Doing so, a response is sent back to us, which we can print. Note that if you are using Python 3, you will need to put parentheses around the print. Executing these lines now, we can see that the result comes back as a file, so a file pointer, fp, which is our CSV file. And so we can read this CSV file directly with the .read, and if we print it, we can see what the format was. So we get the first line telling us the name of the table that has been returned, so table 1, since we did not specify anything. The column names, so RA and DEC, and as our query was just asking for 2 with the top 2 results, so 2 galaxies from our table galaxy, we get 2 lines with the RA and DEC information for both galaxies. In the next exercise, we will load the result of the query into a Pandas data frame. The data frame is a practical format to manipulate results and do data analysis. In this case, we set the query as a multi-line string and set it to the query variable. We can directly pass the resulting CSV file to the readCSV function from Pandas. We specify to skip the first row so that we can directly set our column's name. Once the data is loaded into our data frame, it becomes trivial to plot the results on the sky with the help of AstroPy and Matplotlib. We set the RA and DEC as coordinates on the sky, which we can plot using the Mulvey projection of Matplotlib. We can then plot our quasars as points on a scatter plot. Back on the Jupyter notebook, we can execute these lines. So first of all, the query that we load into a Pandas data frame. And the data frame has a few functions that are quite useful. So for example, we can call the columns by name. So because we've loaded the result with the proper column names, we can directly call it using results and then in square brackets, for example, RA, so that we're only going to retrieve the RA column. Similarly, we can do subqueries as part of our results if we don't want to always query the SQL database. And so, for example, it is possible to construct a subquery using the .lock function from the data frame, where we then specify which column we want to look at for our constraint. And then, for example, if we wanted to have all the quasars that are farthest than redshift of 7, we could set the constraint results square bracket z greater than 7, and then we're going to retrieve only the quasars that are greater than 7. And so finally, once we have our results back, we can then plot them using the functions that we just looked at, and bingo, we have our plot with our quasars on the sky. In the previous example, we only plotted information about the location on the sky. It is possible to add extra information to our visualization by setting the color of the points as the redshift. This can be done by passing the Z column of our data frame to the color parameter of scatter. For instance, here we will set C equals Z. We also stipulate that we want to plot the color bar so that we know what color represents which redshift. Again, we can execute these lines on the notebook, and what we get is a plot of locations versus redshift. For exercise number 3, we will look at positioning differences between objects found in SDSS versus those found in FIRST. To do so, we will simply plot the difference between positions from both surveys. Executing these lines, we can see that there are some small differences in position between the two surveys, where 0 would be no difference. It is possible to download spectrum data from SDSS using information retrieved from the database. The bulk page from the Data Access section informs us that it is even possible to download multiple spectra at once by constructing a text file that lists all the files that we want. This text file can then be passed as argument to the Linux program wget to download the data. In our case, we will use the Python module for wget to download a single spectrum. We saw previously that all spectra are taken from a plate put on the telescope, and that each object is represented by a date of observation and a specific fiber that was put on that plate. Using this information, we can then retrieve the original data. With the result of the query loaded, we can simply construct the path and file name following the instructions that we saw 2 slides ago, and pass the address to wget to download the FITS file. Note that, as we are looking for DR13 data, I modified the core path. Again, we can execute these lines in the Jupyter Notebook to download the file. Once the query is run and the file name is constructed, we can simply start wget and we will download the file locally. We can open this newly downloaded FITS file using the AstroPy module for FITS. Like many FITS files, the file comprises a primary HDU, providing background information about the observation and the data. It also includes an extension HDU, located at index 1, that includes a FITS table. From there, we can plot the spectrum using .data. To plot everything properly, we would need to use the metadata to set the ticks on the x-axis. Other Python packages can be used to simplify this process. For instance, we can use the AstroML package to retrieve a spectrum from SDSS and then use its function to plot easily. In particular, it includes the .wavelength function to generate the ticks values. We can then add some labels along both axes. It is even possible to use latex character with matplotlib to plot symbols such as lambda and angstrom. The result is a nice plot with minimal effort on our part.